Friends and colleagues, I'm delighted to be here talking to you, giving you a very brief tour on gravity. The tour would be very brief. So I'll be talking about my book on gravity. For now, I'd like you to look at this landscape for a minute and ask you if you keep that in mind. Does it remind you of England in any way? So let me start by talking about Newton. Almost basically any talk about gravity would have to start with Newton. Now, in my opinion, physics textbooks have been very unfair to Newton. When I was in high school, I read books and so on and so forth about physics. And typically, the books associate him with action at a distance and saying how bizarre a concept that was. Now, as we can see, in 1693, Newton wrote a letter to his friend Richard Bentley. And Newton was perfectly well aware of this problem of action at a distance. And he said something like that gravity should be such that one body could act upon another at some vast distance, like the Earth acting on the moon through empty space without the mediation of anything else, is to me so great an absurdity that I believe no man who has any competent faculty of thinking can ever fall into it. So the strange thing is that physics teachers are trying to teach children about action at distance all the time. So tell me, in school, when you first learned about the inverse square law, did you not find it bizarre that gravity could act through the vastness of space? If you look up at the moon on a nice clear night, it's amazing to think that the Earth, it could actually be pulling the moon down. And so would Newton have described you as lacking in faculty of thinking? Now, who solved Newton's conundrum for him? It took a while. It took more than 100 years. We all know we are here at the Royal Institution, and you all know who that might be. And it's one of my greatest heroes in physics. Well, namely Michael Faraday. This picture was taken from my first popular book, Fearful Symmetry, which was written 35 years ago. Now, I commissioned an undergraduate art student. I put an ad in the student newspaper to get an undergraduate art student to do the drawing. And just this morning, I was just thinking to myself, amazing how time passes by. You know, I wrote this book 35 years ago, and now this young woman undergraduate is now probably like 55, pushing 60. So anyway, I think we all admire, we're all big fans of Michael Faraday here. But the biggest fan of all is Albert Einstein. And read what Albert Einstein has to say. So Albert Einstein said, for us who took in Faraday's ideas, so to speak, with our mother's milk, it is hard to appreciate their greatness and audacity. And that's absolutely true. Me too. I'm a big fan of Faraday. And in my popular books, I put in a picture of Faraday whenever I could, as you can see here. Now, that is high praise in that, indeed, from Albert Einstein, to compare Faraday to mother's milk. And in some way, a theoretical physicist like myself really do think of Faraday's idea as so important to physics, to theoretical physics, that we could compare it to mother's milk. And what is that idea? It is the idea of a field. Okay, so with Faraday, the concept of a field enter into theoretical physics. But now every little kid who watches movies like Star Wars knows about field of force. And in fact, my son, who's now 9 years old, I remember when he was 4 or 5, he would come over and ask me to use the force of use the force on him, or the field of force. So all I have to do is stretch out my hand like the emperor, and he would pretend to choke. So what did Faraday say? Let's remind ourselves. Faraday said, two charges do not act directly on each other, but they each produce an electric field that in turn acts on the other charge. And similarly, the magnetic field. So here we have a picture of it. This young woman, Peggy Royster, drew a picture. Here are two charges, a positive charge and a negative charge. And the interaction is that this produces an electric field, which then acts on the negative charge. Now, a pragmatic physicist, and you'll be amazed, actually, among the physicists I know, it's incredible to me, actually, how many physicists are so incredibly practical-minded. If there's some idea that doesn't have any utility to them, that they cannot use it in some way, they kind of just don't care about it or dismiss it and so on. They don't even want to hear about it or want to learn about it. You'll be amazed at how many physicists out there working on very specialized stuff doesn't know a thing about Einstein's theory of gravity. This is always an astonishment to me. Now, a pragmatic physicist would be inclined to dismiss all this as just talk. You know, this is worthless stuff. You know, it doesn't advance our knowledge one bit. It's just another way of describing Coulomb's law. But this pragmatic view misses the point. And the important point I'll come to on the next slide. So what's the important point? The real content of Faraday's picture is that the electromagnetic field not only can be thought of as a separate entity, it is a separate physical entity. It can move off on its own. Now, a friend of mine, Anupam Garg, written a textbook on electromagnetism, and his book, he made the following statement just to emphasize this point upon students. He said the electromagnetic field, and I quote, the electromagnetic field is as real as a rhino. Think about that, okay? It's no less real than a rhino. The electromagnetic field, like young people today, could leave home, take off, and live independently of the charges and currents that generated it. That's one of the great discoveries of Maxwell, that this field could literally take off. Without it, our modern civilization would be totally impossible. The age of telecommunication is completely based on this statement. Now, England produced these two great physicists in the 19th century, Faraday and Maxwell. And the interesting thing is that they couldn't be more opposite. As you probably all know, Faraday came out of abject poverty, almost Dickensian. He had no education, so he knew no mathematics. And one of the reasons he invented this idea of the field, which now has become part of physics everywhere. I work on quantum field theory, and I'm sometimes described as a quantum field theorist. That's my main profession, so to speak. On the other hand, Maxwell grew up in a rather distinguished family, I think one of the more distinguished families of that time. But when Maxwell saw what Faraday had written about fields, he vowed not to read any mathematics until after he had understood what Maxwell had to say. So this I love to show to the young theory students today. You know, so for a while, for example, string theory was the height of fashion. It's extremely fashionable. All the young graduate students who come in, they all want to know string theory. They all want to go off and study tons of mathematics. So I love to show them this, that Maxwell vowed not to read any mathematics until he understood what the physics is about, you know, the physics underlying it. And many young people seem to have forgotten about it, especially during the heydays of string theory, now to their regret. So Maxwell realized, as you all know again, great discovery, that light is just an oscillating electromagnetic field. So sometimes I think that Alexander Pope's poem, Let There Be Light, should be applied perhaps more appropriately to Maxwell than to Newton. So once Maxwell realized this, and this is the point I want to emphasize to you, once he realized that light is an oscillating electromagnetic field, then the gravitational field obviously followed. That was Newton's question. Newton wants to know what mediates between the Earth and the moon. And it's the gravitational field, according to Faraday. So it's natural to go from electromagnetic field to gravitational field. And then quite naturally, if you have electromagnetic waves, you would also have gravity waves, oscillating gravitational field, namely the gravitational analog of light. So the great discovery a few years ago, which, by the way, happened while I was writing the book on gravity. I actually signed a contract for On Gravity before the discovery of gravity waves. So in some sense, the timing of my book was really excellent. So, but I want to emphasize to you that theoretically, it's not a great surprise, right? It's almost demanded that once you have an electromagnetic wave, you naturally have gravity wave. And in fact, there were a lot of speculations even before Einstein in the 19th century. And I think one of them was, again, an Englishman, this Oliver Heaviside. Okay. So let me talk a little bit more about this, how gravity wave and electromagnetic wave came by. Well, let's think about something totally different, which is an infinitely rigid rod. Okay, consider an infinitely rigid rod. Then by definition, the whole thing moves as a whole, right? Because it's infinitely rigid. So you hit the rod at one end, that information is transmitted to the other end instantaneously. Okay? But this is forbidden by Einstein. In special theory relativity, everybody in the street now knows that nothing could go faster than the speed of light. So an infinitely rigid rod is forbidden now in physics. There is no such thing. It's forbidden by Einstein's special theory relativity. It's incompatible with relativity. So this is also abhorred by Newton, right? Newton thought that any instantaneous transmission of a cause and effect, if you believe in that, you are lacking in philosophical faculty. By the way, that's become my favorite phrase as well. That's a nice sort of old-fashioned insult that you might launch at a dumb person who annoys you. Anyway, so in physics, rigidity, no. Waves, yes. As soon as rigidity falls, we have waves. So we have electromagnetic waves and gravity waves. And this is not so surprising that waves and rigidity clash. They don't coexist. It's even, you can understand that in everyday terms, right? Undulation. So think about belly dancing. It's all about flexibility. Okay. And a very stiff and stern man could hardly be expected to wave. Okay. So space-time, in some sense, is the last rigid entity in classical physics to fall. And we now know that space-time undulates. So in Newtonian physics, space-time is rigid. And in Einstein's theory, space-time is not rigid. It could move about. So once again, I emphasize to you how gravity wave is almost inevitable. Because once Einstein declared that space-time is elastic, namely that it's curved and it can be bent and not absolutely rigid, then gravity wave is almost like it follows. This is why the overwhelming majority of theoretical physicists had long been convinced of the existence of gravity wave. Nobody was surprised. Furthermore, I haven't talked about quantum physics until now. When you quantized the electromagnetic field, the electromagnetic wave, we know that it consists of photons. And similarly, when we quantize the gravity wave, it consists of gravitons. Now, of course, nobody has observed gravitons yet, but we firmly believe that gravity wave consists of gravitons, and modern theories about gravitation, or people talk about the graviton. And I'll come back to the graviton eventually. Okay, I'm still pushing the wrong button. So here's a happy man. Einstein published his theory of gravity in 1915 and has withstood the test of time. As you know, over the century, there have been many, many tests, and has passed all these tests with flying color. I get extremely annoyed when I see a headline saying some new observation has somehow disproved Einstein's theory and so on. You know, it's almost, you could bet your money on it that it's a total nonsense. Okay, so next slide. So now I'm going to talk about one of the tests of Einstein gravity. As you probably know, Einstein had proposed 3 tests of his theory. And one test was the precession of Mercury. The planet Mercury, as it goes around in its orbit, would precess by a tiny, tiny bit as it goes around, as a deviation from Newtonian theory. The other prediction that Einstein had was that when light goes by a massive body, it would be deflected, it would bend. So, but in fact, this idea was not original with Einstein. That Newton is an incredibly smart guy. You know, every time I think about Newton, I'm just blown away. Newton had wondered and whether a body acting upon light would bend its rays. Now, the history is very interesting, has all kinds of twists and turns, which I would like to tell you about. In 1801, a young German physicist named Johann Soldner, he used Newton's theory. What Newton had suggested was that light consists of a stream of tiny particles. And so he calculated the deflection of light by astronomical objects, okay? And I'm not sure Newton did the calculation, but it would be a trivial one-line calculation for Newton. So he obtained what I would call the Newtonian value, that if Newton had done the calculation, Soldner would have agreed with what Newton got. Now notice one important fact here. We all learn in school that the force, that a gravitational force is proportional to the mass of the particle, but then Newton's F equal to ma, the acceleration of the particle under a given force is also proportional to, is the force divided by the mass, so the mass of the particle of light cancel out. Otherwise, you could ask yourself, how does Newton know what the mass of the particles of light are? So it turns out that it's irrelevant. So they got out some, Soldner published some paper, the young guy. Now, Soldner is probably one of the most unlucky theoretical physicists in history, among them, well, one of the most, because then, as you all know, Maxwell's theory came out, and Maxwell said that light is a wave, and so Soldner was completely wiped out. Nobody's interested in his stuff, so he sank into obscurity. Nobody's heard of him. So in 1911, as Einstein was working out his theory, he was totally unaware of Soldner's calculation. As I said, nobody's heard of Soldner anymore, even though Einstein was German and Soldner was German. They were both in Germany. So Einstein predicted that light would bend in a gravitational field in his theory of gravity. But Einstein, as you probably know, he's by far the greatest physicist who ever lived. In just whenever I read anything by him, it's just incredible. But he made a computational error, and of course anybody could make a computational error. And so what he did is he reproduced the Soldner-Newton result, okay, which he did not know about, as I said, and which would have disagreed with the observation, because Soldner-Newton is incorrect, right? But this is not good for Einstein, because later the Nazis dragged out Solnit's paper, and that was part of their accusation. They accused Einstein of stealing from a pure German. Okay. Now, another interesting footnote in history is that as a naive theorist, Einstein wrote to George Hale, which is the director of the biggest telescope in the world at that time in Los Angeles. And he was wondering how close to the sun fixed stars could be seen in daylight. This is so laughable to me. I mean, to any physicist now, even to you, right? How does he imagine? Einstein is an incredible thinker, but sometimes he says things that you would think is so incredibly naive. Sorry, take a drink of tea. Einstein, so Hale had to explain to him that exploiting a solar eclipse would be much more promising. So let's go watch a solar eclipse, Einstein proposed. Okay. Now the story has even more twists and turns, as you see. There's a book published. So I got this out of this book, Einstein's Luck. So an expedition was mounted. Remember on the previous transparency, I said it was 1911. I remind you, 1911. Well, these dates are important. So expedition was mounted in 1912. The next eclipse was in Argentina, but they ran into bad weather, so they didn't see anything. The next one was in the Crimea and was due on August 21st, 1914. Well, I want to emphasize to you August 1914. Does that ring a bell from your school days? Well, there's a famous book called The Guns of August, which I highly recommend, by the way. So The Guns of August, of course, the guns started booming, the cannons fired, World War I erupted exactly in August, the beginning of August 1914. Now, suppose you are the Russian in charge in Crimea. There are a bunch of German astronomers sneaking around, and they're talking like nonsense. They're talking about curved space-time, and then they're carrying all these telescopes with them. Come on, they're obvious spies. They're obviously German spies. If you're the Russian in charge, you of course would have arrested these German guys and throw them into jail. So Einstein again was saved, and meanwhile, during the war, Einstein found his mistake, that he was off by a factor of 2. And I'm going to come back and talk about this factor of 2. He wrote to his friends saying how relieved he was that he found this error. But after the war, as you probably all know, the great pacifist Arthur Eddington made it his personal mission to show that good physics transcend natural boundaries. As an Englishman, he's going to go out and verify the theoretical prediction of a German physicist. So now, as I said, the general public, one of Einstein's prediction, as I said, was the precession of Mercury, right? But you could imagine the general public, I think they could be excused. The general public could care less about the precession of Mercury. But on the other hand, curved space-time, now that is absolutely amazing. And so overnight, Einstein became a worldwide celebrity. And the story is that without these twists and turns of history, Einstein's triumph would have been a wet fizzle. Suppose the World War I did not happen, they observed the eclipse and then found Einstein was off by a factor of 2, and that Einstein and Newton got the same result, and so on and so forth. So this was a sensation. It was headline everywhere, and I'm going to show you one of the headlines. Now, a few years ago, I visited my friend Freeman Dyson. I can call him my friend, even though we're far apart in age. Unfortunately, Freeman is no longer with us. And he told me that how sensational it was at that time, because Eddington came back, made the announcement, and then wrote a popular book. And he told me that his father rushed out to buy Eddington's popular book, which Dyson then promptly lent to me. Now, Eddington, as you know, probably one of the pioneers of writing popular physics books. So as a writer of popular physics book, I have to pay him my respect here. He does have a way with words that I think captures the reader's imagination. So think about at that time, 1914, people in England are just getting used to the idea of paying their monthly electric bill to pay for electric light. I think by them, I mean, 100% of English homes have electric light, I imagine. So in his book, Arthur Eddington asked the reader, how many pounds of light does a pound buy you? I love this unit, and I, in fact, wrote it into my most recent textbook. I wrote a textbook called Fly-by-Night Physics, and this unit, pound per pound, is just brilliant. For those of you youngsters out there, who high school students perhaps, who wants to sit down and do a calculation, here's the answer. It costs 140 million pounds per pound. Now, so I keep talking about this factor of 2, but again, you might be puzzled a little bit that you might have expected something more complicated. No, you're jumping from Einstein's theory, jumping from Newton's theory to Einstein's theory. So, and it's only a factor of 2 disagreement between these two great masters of physics, the undisputed, the greatest among the greats. So when I wrote my textbook on gravity, I was puzzled myself, and I worked a little bit to figure out where this factor of 2 comes from. Of course, you can just blah, 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 work through the equations and get Einstein's answer. And I imagine somewhere in the universe, perhaps these two greats are having a conversation. And Newton said to Einstein, I curve time. And Einstein said, I curve space also. That's the factor of 2. Now, this is not how Newtonian gravity is usually taught. That in itself is I threw this out here as a puzzle for those of you who are more advanced in physics. How is it that Newton curved time? This was something for you to think about. Okay. Now, I'm going to take a break from discussing physics. You might be tired of hearing all this physics. And so I'm going to take a break and recommend to you a Brazilian movie called The House of Sand. Now, very few people know, by the way, I had this in one of my undergraduate courses here at the University of California. And when I showed this movie, I asked the students, and nobody knows. I mean, very few people know that Brazil, when you say Brazil to Americans, they always think of the Amazon jungle and everything, things like that, samba and carnival. But very few people know that Brazil contains a vast desert. But I do know, for reasons that some of you know. So somehow I know Brazil quite well, and it actually I can tell you it has a huge desert. And in this award-winning Brazilian film, which is about time, incidentally, spanning many decades, starting in 1910, the main character, this woman, who's the director's wife, was wandering around the desert, lost. Her husband had done the crazy thing of building a house in the desert. And she suddenly ran into a bunch of very strange-looking men who were formally dressed, but practically in tuxedos, carrying telescopes wandering around the desert. So then she ended up having a discussion about curved space and time. So I think most of the people watching the movie were totally lost. I didn't know the movie contains this. All I read about was that it's a movie about the desert in Brazil. So this was extremely amusing. So that goes back to the eclipse of 1919, right after the war. There were actually 2 expeditions. Everybody probably, especially in England, I'm sure all of you heard about Arthur Eddington's expedition to Africa. But the Royal Society actually financed 2 expeditions. And the other one was to Brazil and was led by Andrew Crommelin. This poor guy, I'm sure some of you may have heard of him, but I have never heard of him until I wrote my book. he seemed to have sank into obscurity as well, at least compared to Arthur Eddington, who became infinitely famous and infamous. So the reason to have two expeditions, of course, to make sure that it's not wiped out by any bad weather, rain or storm or something. So the Royal Society was, unlike the Royal Institution, is apparently quite flush in those days. So here I promised to show you the headline. And this is the headline in the New York Times on Monday, November 10th, 1919. So imagine these people had passed the weekend, a nice weekend, and then on Monday they pick up the newspaper. And it says the lights are askew in the heavens. But the New York Times actually, in a subtitle, advised people, nobody needs to worry. Okay, so good, nobody needs to worry. And then it promulgates the old chestnut that a book for 12 wise men, that only 12 people in the world who understands Einstein theory. That's definitely not true, even in 1919. So when I found this, when I was writing my book, I'm naturally curious. This is such big news, right? For physicists, this is, huge news that the curved space-time is curved. So finally, we found out that the New York Times announced this result. There must be something similar in the London Times, in newspaper all around the world, I imagine. If somebody would show me the headline in the London Times, I would really appreciate it. So naturally, I'm curious about what's the other big news of the day. Okay, and this is for you to have a chuckle. So the other big news of the day on November 10th, 1919, here it is, right next to this headline, is French government to open cheap national restaurants. Well, we're still waiting. Now, I come back now to physics a little bit and talk about Einstein's motivation for curving space-time. Now, how is it that Einstein would have this bizarre idea of a curving space-time? Well, we have to go back to Galileo's Leaning Tower experiment, showing the universality of gravity. What does that mean? This experiment was repeated in 1971 when an astronaut dropped a hammer and a feather on the moon where there's no air resistance. So according to physicists, the only reason a feather falls more slowly on Earth is because of air resistance. So a hammer and a feather without air resistance should fall at the same rate. And that's called universality of gravity. And it's exactly the same thing that I mentioned before, that the mass, although the hammer is much more massive than the feather, the mass cancels out in Newton's equation. So that was what Galileo was trying to get at, and which led Einstein to curving space-time. So I didn't attach a video here because you could watch it in the privacy of your own home. And it's also, I noticed, on the Royal Institution webpage. But how does universality of gravity get to curved space-time? Well, that was Einstein. Einstein realized that curving space-time could explain the universality of gravity. So let me explain Einstein's idea. And before I do that, let me summarize for all of you in one sentence. So this is really Einstein gravity in a nutshell. What is gravity? What Einstein said was that it's curved space-time masquerading as gravity. That in some sense, gravity is just the effect of curved space-time. So let me explain on the next transparency. So imagine that you are going to take an airplane from, say, Los Angeles to Taiwan, to Taipei. And you fly over the Pacific, and some of you may not be old enough. I'm sorry, but but many of you are old enough to know that in the old days, there's not a monitor in front of your seat, but there is some airline magazine that they give you. And in the back of the airline magazines, they show the flight path the flight is taking. So you sit down and you look at the flight path. This is very odd. It looks like there is a force pulling the airplane north. So next time you take a different airline, and you see that it follows the same flight path. What's wrong with these pilots? They don't have any sense of personality, originality. Why don't they sometimes just fly south over Hawaii, and instead of bending over like this? Why are they following a curved path? Okay, well, you laugh and you chuckle, and you know the answer because you're the type of people that come to the Royal Institution talks, right? I don't want to ask the guy sitting next to me. I mean, he wouldn't know anything, most likely. But the point is, of course, we all know this map is a flat representation of a curved space. Okay, the surface of the Earth is curved. So Einstein realized the same thing. Space-time is curved. That shows that the particles are all following straight lines, and the straight lines looks curved in space-time. And they all follow the same path. That's different airlines going the same flight path. And so universality of gravity follows. Okay, so the hammer is going this way, and the feather is also going this way, the same way. Okay. So, but now then, Einstein and others, Schwarzschild in particular, once they realized that space-time could be curved, they realized excessive curving might be dangerous, that it would lead to a black hole. And I think most of you know if the object is too massive for its size, it becomes a black hole. And this is the criterion, mathematically Newton's constant, capital G, multiplied by the mass of the object divided by c squared. C is the speed of light. If that is greater than the typical size of the object, then this object is a black hole. And this was first proposed by the Englishman Mitchell and the Frenchman Laplace. And here I plotted this obesity index. On the vertical axis, I have the logarithm of the mass of the object in grams, and in the horizontal axis, the logarithm of the size of the object in meters. And you see that everything above this line is a black hole, and everything below not. So you see that humans are very far from black hole. The Earth is a little bit closer, and the sun is even closer. The Milky Way is closer, and the universe is almost on the verge. So what is a black hole? All I ask you to remember is that even light cannot escape once it gets inside the horizon of the black hole. So please remember this term horizon. So the term horizon is used because in the old days, when ships go over the horizon, you cannot see them anymore. So when a person falls inside the horizon, you cannot never see that person again. That person could never get out because space-time is curved so much. So I talk about space-time, but what is the curvature of space-time? How do we measure it? Now think of a creature living on a curved surface. When we think of a curved surface, we naturally think of it as contained. The technical word is embedded, the mathematical word, in the three-dimensional space we live in. So we can easily see whether the surface is curved. We just look. But the creature who lives on the curved surface cannot get out of the surface and take a look, right? This is a misprint. Take a look at his world, not his work, and his world any more than we can get out of the universe and take a look. So what can the creature do? So what is the mathematics of measuring the curvature of space-time? So I explained that by giving you a riddle that I came across as a kid, as a child. I just tried this out on my 9-year-old boy the other day. Here's a riddle. A man walks due south for a mile, then walks due turns, and then walks due east. And then he walks for another mile, and finally he turns north. After walking for a mile, he arrives back at his starting point. He gets back to where he started from and where he saw a bear. He sees a bear. What color is the bear? Okay, that's the riddle. This is taken from my book, Einstein's Universe, Oxford University Press. So some of you know the answer and some of you don't. I tried on a lot of people. Most people cannot figure out the answer. The color is white. So most people said, how is that? You didn't tell me enough. How do I know what the color of the bear is? Well, you can see that if the guy walks due south, due east, and then north, and he comes back to where he started, that could only happen if his starting point was the North Pole. He walks south, east, and then north, okay, to form a circle. So in mathematics, this concept of walking in the same direction is called parallel transport of vectors. Mathematicians like big words. Okay? They don't want to say walk in the same direction, but they say that we transport vectors. So vectors is a direction, okay? And parallel transport means that you walk with pointing the vector in the same direction. And the relevant mathematics was developed by the German mathematician Bernhard Riemann. And you measure curvature by parallel transporting a vector over a closed loop. Okay, so I just explained to you that's the basis of Riemannian geometry, which luckily for Einstein, Riemann had worked it out. It was just there ready for Einstein to use for his curved space-time. So we talked about parallel transport of vectors and curvature. But in the ancient Chinese chronicle, in some ancient document, this is before the compass was invented, okay? So no compass. The emperor was going into some battle, and some astrologer told him that there would be fog, and so he wouldn't be able to see which way is which. So he had a physicist build him a carriage, and this carriage is amazing. It has a pointer on it, and it always points south. So with this carriage, the emperor knew exactly what direction he was going in, and so he vanquished his enemies, and the physicist was given a huge reward and given tenure and so on and so forth. So, but incidentally, another footnote to this is that the design for the carriage was lost in the Chinese historical documents and lost for centuries, 2 millennium. And so there was a contest held in modern times on how to build this carriage. And as I remember, I'm 100%, 99% sure I was right, that it was won by a British engineer, but I read about this a long time ago. So I went down to the physics department machine shop, and as a theoretical physicist, I hardly ever go into the machine shop. That's where the experimentalists had all kinds of fancy equipment built for them. And Louis Grace, who was in charge of the machine shop, this gentleman, was very surprised to see me there. So I asked him to construct for me the Emperor's self-pointing carriage. And here it is. And some of you maybe who are mechanically minded might try to do it at home. See if you guys could construct something like this at home. So for me, the Emperor is, of course, Emperor Albert. So I have this in my office, and every time a student shows up and asks me what it is, I could push this carriage around, and it could curve and go around in different directions. And the Emperor's arm is always pointing in the fixed direction. Well, you can see how it works, right? Because the two gears is going to drive this gear and so on and so forth. Okay, I'm running out of time, so I'm going to hurry up a little bit. So I'm going to turn to my next topic, and I'm going to introduce quantum physics now. I mentioned quantum physics, but I haven't talked about it. So I introduce you to the square of physics. For the moment, we're not going to talk about gravity at all. With gravity, it would be the cube of physics. So I classify all physical phenomena without gravity into the square. So the horizontal axis, I have plotted the size of the characteristic size of the objects involved, big to small, slow and fast. So we live in this lower left-hand corner. This is a large lumbering objects moving very slowly through space-time. That's us. That's governed by classical physics. Now, if you have a rocket ship going near light speed, that's a big object going very fast. You need special relativity, but you don't need any quantum mechanics. On the other hand, suppose you're in a very small object, an electron, moving around an atom. By the way, in a hydrogen atom, the speed of the electron is about 1% the speed of light. So it's definitely slowly moving. There's no need for special relativity, but you certainly need quantum mechanics. Now, in the middle of the 20th century, physicists try to move into this upper right-hand corner. This upper right-hand corner, you have small objects moving very fast. So you need both quantum mechanics and special relativity. And the marriage of these quantum mechanics and special relativity produce quantum field theory, which leads to an entirely new physics, which I'll now explain. Physics that's not here and not there, okay? So this is taken from one of my popular books. In every area of physics, there's a gold-plated equation. And the gold-plated equation of quantum mechanics is Heisenberg's uncertainty principle, which says that the uncertainty in energy and the uncertainty in time is related, inversely related via Planck's constant. And I like to explain this I explain this in my popular book by an embezzling analogy. So consider an embezzler. So what this says is that the larger the accounting error, the sooner it'll be detected and set right, right? So this delta E that I have here, the uncertainty in energy, I think of as an accounting error. And the larger the error, the sooner the mistake would be found, and vice versa. So the advertising slogan that goes with the uncertainty principle is that accounting errors could be tolerated for a short time. So in this respect, the quantum world is actually in accordance with the garden variety everyday world. And in fact, I read somewhere in some magazine that a surefire embezzling scheme that might not be detected for a long time is to skim off a penny at a time. Okay. Now, so students in a course on quantum physics, they learn to deal with these fluctuating uncertainties all the time. So there's, for example, the energy is fluctuating, uncertain, but always over a very short duration. And what can these things do? Actually, nothing all that much. Imagine having the students in some quantum mechanics exam calculating the behavior of two electrons in a box. They could calculate till they're blue in the face, but there will still be two electrons in the box, not one more, not one less, okay? The quantum fluctuations cannot do very much. The next area, the other area, amazing area of 20th century physics is special relativity. And it's the gold-plated equation associated with that is, of course, E equal to mc squared, which tells you energy could be turned into mass. And the advertising slogan is that counting errors could be turned into stuff. Then again, I use my embezzling analogy. So energy could be converted into mass and hence particles, according to Einstein. So our proverbial embezzler could then turn an accounting error into a Lamborghini. But only in his dreams if the world is classical and not quantum, right? Because in the classical world, there is no accounting error. There is no fluctuating energy. Energy is energy and energy is conserved. There's no way for some Lamborghini to pop up. So we have two separate strange worlds. They're both very strange compared to everyday life, right? Quantum mechanics and special relativity, but they're not strange enough. And the fun really begins when physicists combine the two. So as I said, when you combine the two, you get quantum field theory. And I've written a fairly widely used textbook on quantum field theory for those of you who want to learn something about this subject in 2003, and I'm now working on a popular version of this book. So what happens when Dr. Heisenberg meets Professor Einstein. So in quantum field theory, a state of nothingness is known as the vacuum. But nothingness does not merely contain nothing. That is one of the most amazing aspects of quantum field theory. To the contrary, in some sense, it contains everything. Because the vacuum is a roiling sea of quantum fluctuations, boiling with particles and their corresponding antiparticles, right? They come into existence from nothing, and after a short while, poof, they go away. The particles and its antiparticles vanish, and physicists say they have annihilated each other. And how long they last is determined by the energy of the particle, antiparticle pair, in accordance with the uncertainty principle. So to summarize, when you have both quantum physics and special relativity, the energy fluctuation could turn into stuff, could turn into matter, but it can only last for a very short while before it disappears back into thin air, okay? So again, in our embezzling analogy, our embezzler got the Lamborghini, but the magic could last for only a very short time before the fairy godmother's carriage turns into a pumpkin, so to speak. So how to avoid this? How do you get to keep the carriage? How do you not have this happen? There are two possibilities. So again, in our analogy, the question is, what could our embezzler do? Well, one is you can pester the government to build some high energy accelerator so that there's a lot of energy flying around. And you guys have all heard about all this, that physicists are always bugging the government to build these accelerators. So the analogy in our embezzling scheme is if there's a $1 zillion account lying around and zillions of dollars are moving in and out, then you take off a little bit of nobody would notice. So in a high energy accelerator, there's a lot of energy around, so we borrow a little bit of energy from the beam. By the way, my oldest son is an attorney with the Department of Justice in the United States, and he worked for a federal judge in New Orleans after Hurricane Katrina. And he told me it's incredible. At that time, the Bush government was pumping in billions of dollars every day into New Orleans. Well, if you're in a position to take off with 100,000 here, 100,000 there, nobody would notice. What is the second possibility? So the first possibility is kind of obvious, build high energy accelerator, which is sort of the standard thing in particle physics. You're probably bored hearing about it, LHC, all this stuff. At least I'm terribly bored. But the second possibility is you curve space-time. You go near a black hole and you hide stuff in there, okay? So the embezzler, again, back to the embezzler analogy, an accounting error could be turned into stuff if a slush fund is hidden in some dark corner of the bank where no inspectors ever venture. Or if an inspector venture there, he's trapped and cannot escape to tell the tale. Black hole is perfect for this. So, but this was not obvious. As I said, the first possibility is obvious for a long time, but this second was far from obvious and has to be thought up by somebody. And it was thought up by this amazing man in a wheelchair, a truly amazing guy, just the willpower. So this is taken after a lecture I gave in Cambridge in 2011 about, well, it's almost 10 years ago, about some crazy idea I had about gravity. And there's Stephen Hawking, who unfortunately is no longer with us. And there's me, in case you're confused. Okay, so let's talk about Hawking radiation. Now I'll try to explain Hawking radiation to you in one transparency. And I think I can do it. I'm running out of time, but I'm almost done. A quantum fluctuation near the horizon of a black hole produces a particle and its antiparticle. But because of the uncertainty principle, we can't be sure whether it's inside the horizon, outside the horizon, maybe they're both outside, one is inside, okay? So let's suppose that the antiparticle is inside the horizon, then it falls to its doom, never to be seen again. But the particle that's outside the horizon escapes. So an observer far away from the black hole would see the particle coming from the black hole. And he concludes that the black hole is radiating particles. Now, equally well, we could have the particle being inside the horizon and falling in, while the antiparticle escapes. So the observer far away could see the black hole radiating equal streams of particles and antiparticles. By this argument, you see that the number of particles coming out, the number of antiparticles coming out, have to be exactly the same, okay? So because the black hole could care less about what you call a particle and what you call an antiparticle. So in a one transparency, this is Hawking. Well, in hindsight, everything is obvious, but believe me, in 1974, it was not obvious at all. Okay, so this brings us to the end of our tour. I'm going to summarize for you a little bit about gravity. Okay, so let me summarize gravity by having a child ask a panel of experts, why do we all fall down? Well, the first person on the panel is Aristotle. He said, well, the earth is the natural home for rocks and men. That's literally what he said. And the rocks fall because they want to go home. And in fact, Aristotle's theory makes even a prediction. He said, well, you notice that rocks fall, they go faster and faster. And if you've ever been to the far west in the United States, you see there are a lot of rental places where you can rent horses. And tourists would rent a horse, and after a long ride, as they come back to the stable, the horse could sense that they're going home. And so they break into a gallop and start running faster and faster. So that explains why rocks go faster and faster as they fall down, right? And so Aristotle says to the child, when you jump out of a jungle gym in the playground, you are really expressing your inner desire to go home. Okay, you try to explain that to a little kid, as I have, and they said, this is nonsense. I didn't say I want to go home. I want to play some more. So the next expert is Newton. That Aristotle fellow is totally full of baloney. I've interviewed plenty of rocks, and they never say anything about going home. And rocks and apples fall because they and the earth and every other object in the universe exert an attractive force on each other. And this is what Newton says to the little kid. As you jump out of a jungle gym, you're actually also pulling the earth up. This is Newton's third law, right? The action and reaction. And I remember when I first learned about it, I always had trouble about thinking about this. But it's true. When you jump out of a jungle gym, you're pulling the earth up by you're exerting a gravitational force on the earth. So next is Einstein, who says Newton is so right. But there's a lot more to the story. The force that Newton talks about actually comes from the curvature of space-time. So the earth is warping the space-time around the jungle gym. So Einstein said to the child, when you jump, you are actually looking for the best possible path to get through space and time, the best deal for yourself. Now comes the quantum theorist of gravity, the contemporary quantum theorist, says Einstein somehow find the quantum world distasteful, even though he was one of the founders of quantum physics. If he weren't so stubborn, he might have realized that his curved space-time is just due to gazillions of gravitons sashaying around. When you jump out of the jungle gym, gravitons zing back and forth like crazy between you and the earth. So leave Aristotle aside. I really don't think what he said is right. The other three are all perfect truth-sayers. So as a joke, I'm always, when I give this popular talk, I'm tempted to invite Darwin to join the panel also. So I hope the audience in England wouldn't be offended by this joke about Darwin. So Charles Darwin, if he were on the panel, he would say, I'm not a geologist, so I can't tell you why rocks fall down. I could tell you how apples fall down, why apples fall down. There used to be apples which fell up and others who fell down. But the ones who fell up into outer space, they did not get to reproduce. So apples evolved to all fall down. Okay, so with this joke, I end my talk. And I want to say that for those of you who want to learn more, this is a very brief talk. And as you can imagine, the book itself is very brief, very small book. And the talk itself is just hitting a few highlights in the book. So there's a lot more in the book than my talk. But for those of you who want to learn more and who happens to already know some Newtonian physics and calculus, I strongly encourage you to try to move on to my textbook. What I always tell people who write to me is that you can read 100 popular books on physics, but unless you see some equation and you actually look at the textbook, you're not going to really understand what's going on. So you can see, now you see where the landscape in my first transparency came from in my title. It's this top part of this landscape. So I can now tell you, this is a painting I commissioned by a friend of mine, the British painter, the British artist, Jane Callister. And please Google and look her up and support her work. She is British, from the Isle of Man, and now living in Santa Barbara. So from her, I've learned all about Isle of Man and that the people there have 3 legs and all kinds of interesting facts. I couldn't wait to visit the Isle of Man one of these days. So thank you so very much for listening. Thank you.